Hello everyone and welcome back to TritonTv. We got a special video for you today. This one's pretty technical, so most people probably won't care about this, but I got to help a coworker with something very similar on Monday and figured I'd make a video so I could share it. And yeah, so I believe the title of this video is going to be something like C-axis clocking on Okuma CNC machine or something like that. So I'm just going to explain visually where the need for this arose and why I'm doing it like a brute force, write my own code way. So I have a program here that I wrote from scratch, um, and I'm going to explain graphically where the need for this came from. So let's do this actually. Let's open Okuma Set and Inspect, which is a probing software used for Set and Inspect works for Okuma as well as Mazak machines, I believe. This is a newer version than what I use at work, so some of the codes are different, but the same logic applies. So basically, I needed to, let's just look at the red lines here and I'll explain this. So I needed to align two lines in the machine on certain, you know, features of a part, and there was something in the way, in this case a boss. I'm not going to really go into the geometry details for reasons, but the built-in probe cycles for the machine, like the rotary axis updates, don't have, I think I have this set up as an ANC machine because I'm running a Okuma MU5000VL, but you know, this same software works with BNC. This built-in cycle doesn't have any avoidance. It'll, let's do this. Yeah, so we're doing a C-axis with X plus probing. You see X here. And the way these native cycles work is you give it a distance of, let's say, 3 inches, right? Just pick some number here. That's the distance here between the points that it picks. And the setup I have in the machine is I'm machining on center of C-axis rotation. And so it's actually really easy to brute force what I want to do. And the need arose from this cycle here doesn't have avoidance built in. I can't just tell it, hey, you know, start up here, move over, come down, probe, come back up and do it. Otherwise, I probably would have just used the built-in cycles from the machine. Let's just see what this looks like, actually. I think I have, yeah, let's go ahead and send this. And then we'll, oops, we'll view that. I believe I have it set to output to, yeah, here. So, and it looks like this is using different cycles than the machine network. Either way, it just didn't give me what I wanted, so I went ahead and hard-coded some stuff that worked on my own. So I'll explain the concepts and then we'll get into it. So this is the ideal scenario, right? We have our part, and this line is at x0 as well as x0. And in reality, what I was machining, you know, this had some width to it, and I wanted, these were important to get clocked right. And this is, you know, the ideal version of what we have, and this is reality, right? So you can either be, you know, clocked slightly positive in the counterclockwise direction, or the other direction as well, like if we were to mirror these about, I guess, the y-axis. So we'll say the red is the ideal scenario. The white is positively rotated and the blue is negatively rotated. And what I mean by that is if the actual surface isn't lined up and I were to go look at it, it's like, oh, the X point way up here is some amount. So here's the theory of how I built this cycle. We'll go ahead and get rid of the blue lines and how it works. And yeah, so in the machine, we have a 6mm probe, right? And we'll just pick a point here in the middle. And just to be different, we'll give it a green color, right? And then we'll move over 3mm, right? And we'll go ahead and rotate this 180. Okay. Actually, I kind of lied there. Whatever. We'll just get rid of this one. Anyway, I need to probe these points. We're going to do this again. Sorry. Here we go. We're going to do blue. And we're going to create an arc 6mm. We're going to create it on here. Here's what we're going to do. We're going to hide our real geometry and we're going to go off the ideal geometry. And then it's easier to explain the theory here. So let's say we wanted to pick up a point on the middle of, okay, there we go. This is basically what it would look like, right? So we have a 6mm probe and we're trying to probe a tangent point in the middle of this line. So if the y-axis value to our probe point is 1.5, that's an important number. We don't really need to do much with it right now. It's an important number, right? So let's do this. This is our c-axis clocking theory, and then we're going to create a new level, and we're going to call this trig functions. Right? We don't need to know them all, but we'll just kind of talk about a little bit of trigonometry here because this is the whole theory behind everything. We'll go ahead and get a 1.5 inch line. And oh, why is it giving me an angle? That is so weird. Here we go. I don't know why it gave me an angle. That is so weird. There we go. So we have our 1.5 inch line. Yes, we're in X. We were in Y earlier. Don't worry about that. And what we'll do is we'll go ahead and give it, let's say it's off 10 thou, right? This is just kind of the theory side of things here. Okay. So we'll go ahead and make that line, uncheck this, and now make a line to our real point, right? So this is how the theory works. All I want to know in my probing cycle and in my logic in the machine is what is the deviated angle from where I should be to where I am? And this is where trigonometry comes in, right? So we know that the length that we are going to be looking, the numbers that matter are going to be this distance and this distance. I literally care not about the actual hypotenuse of the triangle, right? So if we look at our trig functions here, right? We got sine, we got cosine, and then we got tangent, which are your three main ones, right? There's three more, obviously. Sine looks at the, if this is our angle here, it looks at the opposite and hypotenuse, right? We'll go ahead and do this, opposite over hypotenuse. I'll just put that there. Whatever, there's our sine. Oh, good thing I'm not a, and then cosine is adjacent over hypotenuse, right? And then tangent is opposite over adjacent. Okay, so we're getting close, right? If I look at this triangle here, first question is what piece of data do I need to get this angle here, right? These functions typically give you lengths of the side, and then when you do the inverse, the -1 function of these, they become arc sine, arc cosine, arc tangent. And all they really are is you flip these over, right? What's the point of that? Okay. Arc sine, arc cosine, and arc tangent are good at getting the angle. That's the function that we need. And in this instance, we're actually going to be using arc tangent, right? Because we're working with the opposite and the adjacent. And then we're actually going to be using the arc tangent 2 function on the machine. I was reading through the programming manual, and it's just a function that made sense, right? Because I know the length of where I'm probing is 1.5. The deviated x value, I know this is y, but here, we'll do this. We'll rotate this guy. We'll rotate this 90 degrees. Okay, this is the actual scenario that we're looking at here, right? This line here is our our x or y distance to our point that we're going to be probing on the part. And this x distance is our deviated linear distance, and it could be positive or negative. So this entire length here could be over here, right? And we need to build some logic into our cycle to do that. So I know this is a lot of theory, but you have to set up the groundwork in your mind before you know what you need to code, okay? So we're not going to be working with sine or cosine. We're going to be working with inverse tangent or arctangent, right? Tangent. So this is actually going to be the software is not meant for teaching. Let's do this here. So instead of opposite over adjacent, we're going to be doing adjacent over opposite, right? There we go. And this function here, and like I said, it's actually the second tangent, which is actually a function used in video games. I didn't realize that until I watched some videos that broke down that. Anyway, we're going to be using the arctangent function to get the angle, right? So if I know this distance and I know this distance, I can use the arctangent function of those two lengths to give me this angle here, right? So this is all the theory crap. Sure, we'll go ahead and save it, and then we'll actually look at the part. So on our part here, we have our theoretical point that we want to probe, which is right in the middle of the line. I believe I drew it at, yeah. We're in the middle of this line, which is some length, and we're trying to avoid this thing, which is some diameter. And yeah, this is one of the realities where we're positive, and there's the negative rotation. So let's go ahead and look at the code, and then it should make a lot more sense here. So I like to hard code offset checks. This is totally not necessary, but in this instance, we're going to be working with program O3004. I like to keep track of my program numbers because I have a spreadsheet at work where I keep track of my subprograms. This is a subprogram. On the machine, I can register O3004 as a library program and just type in, let's see, yeah, call. Call is how Okumas do subprograms, right? This is the program number. So on my machine, I can just type in call 3004 and it would run this function. All right, so let's go ahead and run through the code and then we'll get into more of the theory. Just ignore this offset check for now. I just put some numbers in here. And in this case, it'd be offset 3. So this is where the function actually starts here, right? And just to explain how if statements work on Okuma machines, if this statement is true, do this. This is the same as a go-to line. It just doesn't need to be explicitly stated. So if this condition is met, as in if offset x, if the x offset for offset 3 does not equal 0, go to nx set. And n followed by something is just a pointer. It's just, hey, go from here to there. And the theory is basically, if any of these conditions are met, just go over here and hard code the offsets, right? So this is, if this doesn't equal this, go ahead and set it to that. Anyway, in my programs, I like to define the variables that are being used. So let's go ahead and look at the variables here, right? On the machine, depending on how you set up set and inspect, let's see if we can get back a step. Yeah. Back. Settings. Okay, so here's our handshake. We'll see that here in a second here. In set and inspect, you can go to the configuration. And here we go. This is all we're looking at right here. This setting here tells the machine, hey, start with VC, stands for common variable. Start with variable 195 and go from there. We don't really need to know much other than those are the variables. And at work, I have a little spreadsheet where I've decoded what different probe cycles, how they use these variables. And in this instance, all we're really going to use, I believe, is VC 195. Let's see if it'll highlight this. No, it's in parentheses. Anyway, we'll get to that. So I define my variables, and these are your comments. Anything in parentheses for this particular setup is comments. So I just say, okay, we're using this. We're not actually using that, but it's still here. So VC 195 is what the probe cycle is going to spit out. So if we go back here, and we do x-axis x plus blah, 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 and then we send it. And then let's see if we can open, yeah, G code. Oh, wrong one. Don't look at that. Sucks too, because these are different cycles. Anyway, you can see PL 195. That's just telling it which variable to start with. Anyway, so this variable is important here. I need to store it. Here's how the function works. We take a point. Let's do this. Let's make this here and this here. And then we're going to turn off all of these managers. Okay, so here's how this works. We're going to probe a point here and here. We're going to save the first point as VC11. We're going to save the second point as VC2. Then we're going to average those 2 points. What does that do? That gives us the aligned, that gives us the best we can get those 2 points aligned, right? In this instance, I'm working on 3D printed parts, and so things aren't perfect. And I just need to know, if I take these 2 points and I average them, that will give me the best distance in X, either negative or positive, depending again on if this surface is rotated this way or the other way. It'll give me the best possible alignment that I can get, right? I just need to know what's the best I can shoot for. Then what I do is I take the first point that I probed. I actually don't use the second point after this. Once I get the average, I don't even use the second point. You could do all kinds of crazy stuff, but this is good enough for me. So I take the, yeah, so 0.3 dev from actual. So I have my actual, and then I have my average, and what I do is do some math and figure out how far is the point from the best clocking that I could possibly get. Basically, what's this distance here? From, you know, where the thing gets lined back up, where both of these are lined up in the y-axis. How far am I, right? And then we have another variable here where it's our arctangent angle deviation, right? This is an actual angle value. It's in degrees. And then VC16 is just a sanity check that I wrote, which gives me the angle deviation from the last time the offset was checked. So we'll just run through this function really quick. So we got some globals. I'm not going to explain too much what those are. These are just setting up the machine. Then we have our tool change on this machine. It's a 6mm probe, tool 999. Blah, 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 more globals, more globals, more globals. We're actually working, this should say H3 actually. We're actually working in offset H3. So we'll go ahead and change. Yeah, all this is 3. I don't know why that's probably because I copied it from a different cycle with a different offset. Anyway, so we go ahead and rotate the machine to A0, C0. We lock the tables, and then we call up the height offset for our probe. Now is when we actually get into the meat of what we're doing. In this instance, we're going to y 1.5 x minus 0.375. And what that is it's a point somewhere over here at the y 1.5 off of the surface, right? This minus 0.375 is what I determined would be away from the part, but close enough to hit with the cycle. And then we come down to 1/2 inch above the part, and that would be from this view. So we'd be somewhere up here, somewhere over here. And then there would be a program stop. And then I always write a note, just says, hey, clean the part. And then in this instance, we're going to measure the first point. This is the distance that I determined to go down to the surface because this was a boss. I'm not going to draw it just because. Then here's our actual probe cycle. It's going to be different than what I would be able to output with this version of set and inspect. But all that really matters is, I believe this is our axis here. So 1 is x and it's positive, so we're probing x positive. Start with variable 195, blah, 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 blah. This is the handshake, basically says, hey, cycle hasn't ran, cycle has ran. And then we're going to turn variable VC11 into the probed result. And the reason why I always do that is this is going to get overwritten as soon as I do a probe cycle. Then we move up above the part, up here. We're still back here. We move up, right? And then we move down to our other probing point in Y, and then down to the same Z value of this point. Then we run the same exact cycle. And in this time, we're setting VC12 equal to the X probed point. G30P2 just brings the machine home, gets the tool out of the way, and then we go back to A0, C0. So now here's like the meat of the cycle. This is where all the theory and everything comes into play. So, as I mentioned before, VC13 up here is our average from P1 and P2. So we're going to set VC13 equal to the mathematic equation, add the two together, divide by 2. It's just an average, right? Now we take our VC14, which up here is defined, is going to be our deviation. It's our 0.3 deviation, right? Our 0.3 doesn't actually exist, but it's our theoretical best alignment up here on this side. I'm doing all the math up here. I don't care about this other than to get the alignment. So we set VC14 equal to our original point minus the theoretical alignment. And what that gives us is that gives us this distance right here, from there to there, right? Okay. And that distance is extremely important because that's what's going to happen with our actual math. Then from this point, we need to have some logic because like I said, we could either be on this side of the line. Oops. We could either be on this side of the line. Let's mirror, actually. Yeah, let's do this. Let's mirror this guy. Yeah, about the y-axis. Okay, so our white is the positive rotation and our teal is the negative rotation, right? So we need to figure out what side are we actually on because both are possibilities. And by eyeball, which is how I was lining this part up, I could be either or. So the first thing we do, once we get all of these, we have now defined these variables right here, like actually in the machine controller. We've got our first point, second point, the average, and then we have our new point, which is where we're going to do our math, which is how far are we from that perfect alignment that we can get, right? Or theoretical alignment that we can get. So the first thing we do after we set that point is we do a check. We say, hey, if this variable is less than 0, meaning is it negative, go to n neg. Otherwise, just keep going, right? So if it's positive, it's just going to run the n pos part of the function, and this is our c-axis deviation. So now we're moving along the tree of variables, and now we're setting our VC15 variable equal to, oh, I lied, it's the a tan1 function, not a tan2. So we're going to set our VC15 equal to the arctangent of our deviation from where we are to where we determined is the best alignment divided by our distance that we probed, because in this context, the way the machine wants the distances is it wants the little one divided by the big one, right? So if we go back to our trig function, we can do this, adjacent over opposite, right? So we have, let's see, this is our angle, this is our opposite, and then this is our adjacent. Oh yeah, it's backwards on this machine. In normal math operators, we would give it this number and then this number. For whatever reason, the machine wants the other way around. So we're giving it this distance here, our x-axis deviation from where we should be to where we are, divided by our linear distance that we probed at, because that's the only way to get this angle here. We need both of those pieces of information. It's just a quirk with this machine, okay? It's just how it works, and it works. So once we set that variable equal to the arctangent of those two distances, we're going to round it up, and I believe by default this rounds it up to the 4th or 5th place decimal. I don't need that many past that. Then, since we've actually gotten the angle, it just says go to rotate positive function, right? And if this check was true, this is where we would be. And the only difference between the positive and the negative is I invert the number. I already know it's negative once I hit this point, so the logic check has already happened. So the first thing I would do is invert the number by multiplying it by -1. And then the rest, this here, is the exact same as this, except for the pointer at the end, right? We already know we're negative. So let's say we're positive. We would get our angle calculation, and then we would go to rotate positive, right? Here's our rotate positive function here. So the first thing we're going to do now is take our new variable, which is going to be VC16, right? And we're going to set it equal to the C-axis offset for offset 3, right? And I have a comment here, save old C-axis offset, because we haven't done anything to it yet. So this is a snapshot. Where are we at right now? Now what we do is we take our C-axis offset for the third offset, and we set it equal to that same offset minus the calculated angle that we got here. And these might be inverted, but they work, so I haven't changed them. And what I mean by that is the only difference between our rotate positive and rotate negative is one's adding the angle, one's subtracting. It works for me. I don't care at this point. So I'll run through that again. Set a new variable equal to your old C-axis offset just to have a baseline. Now set our C-axis offset equal to what it is now minus our calculated angular displacement up here. Up here, I guess, if we want to be pedantic. And then go ahead and update that variable equal to what it is now minus what we set it to before. This is kind of the cool thing with variables having a snapshot is we're using the same variable on this side and this side of the equation, but it doesn't set it until it's used this in the function. So it's almost like getting to use it twice. Anyway, and then the next condition would be if we were negative, do the exact same thing, save the offset, and in this case, add the angular displacement, and then go ahead and keep track of how far we changed it. And yeah, so what that function does is, like I said, I'll just run through it again. Let's go ahead and get rid of our negative scenario. So this is representing our 6mm probe, probing at a position of y 1.5, right? And then whatever the value is. This is the ideal condition here. The red, remember, is our straight lined, and the white is the positive scenario. So if you probe and you're on the white line, you will have points that are going to be, this point is going to be more negative, and this point is going to be more positive. I realize I'm clicking at the end of the line, not where we're probing, right? And so just to get an idea too of the angle, I think I did. Let's measure the angle of these two lines here. I think, yeah, 2.5 degrees. Yeah, so it would pick up those 2 points, figure out how far away from where we probed to where we should be. And it's not going to be this perfect line. It's going to be, how do I get these 2 lines lined up, right? And in reality, they were actually not perfectly on center. They were off to the side a little bit. Anyway, so it would pick that up and then figure out the angular displacement and then rotate the angular displacement, all while keeping track of it. So hopefully that makes sense. It's a really cool function, and I've used it in both the X and Y axis. And now that I have the function built out, it's really easy to manipulate if I need to change something, right? This is picking up 2 points in X. I had a similar part that I was picking up in Y, and I really didn't have to change much other than where I was probing and whether or not the values were positive or negative. And then, yeah, I think I was probing at the same distance too. So I didn't even have to change any of this stuff here. It's pretty cool. So once you get this baseline, now you have a hard coded macro rotating offset. And it's something I'd always wanted to build. I worked with another coworker on a Haas machine, and once I got on the DMG machines, they had that clocking cycle. Let's see if we can go back a little. Yeah, they had a clocking cycle like this. The DMGs are a lot better than this, but I wanted to write one for the Haas machine, and now I think I have the tools to do it based off of how I wrote this function. So anyway, just an example of how I took a problem that I saw at work, and it's something that I'm doing over and over. It's not just once that I do it. I do not want to hand clock these. I want the machine to figure it out for me. It's going to be much more accurate, way faster, and it keeps track of it, all without me doing much. I just type in call O, oops, 3004, and then it go ahead and does the function. It's pretty neat. That's it for Triton TV. Totally more technical video than I've ever put out on YouTube. This is the first video that I've ever done where I've shown something that I've hand coded. Yeah, hopefully you learned something. And if anybody has any questions about these functions or similar functions, feel free to ask in the comments. I've built some really cool macro programs on Okuma machines that work on both the OSP 300 controller and the OSP 500 controller. That's it for Triton TV. This is how to hard code a C-axis clocking probing cycle using X probing points. And you could just as easily probe a web. So you can probe a point on this side and this side, as well as this side and that side. And the reason why it really worked really easy on my setup is my part is set up on center of C-axis rotation. Very, very, very important for how this works. Otherwise, you'd have to do a few more things. Anyway, that's it. Thanks for watching. Hopefully you learned something. Don't forget to smash the like button, subscribe for more, and we'll see you guys on the next one. Bye.